Okay, so hi everyone. Today I'm going to show you what we've been doing in terms of visualization in the COVID on the Web project. So for those who don't know what the project is, I'm going to resume it very briefly. So the project basically, the goal was to, I realized I didn't really prepare it. The goal was to enrich and process the core-19 dataset, which contains a lot of scientific publications surrounding the subject of the COVID-19, so SARS-CoV-2 and other coronaviruses. So we have a lot of people from the team that is involved in this project. And me particularly, I'm involved in the part of exploring this data by the users or using with other applications. So basically what I'm going to show you today is the RVs and LDVs applications. So I'm going to start with the RVs application. This is has been developed to support the exploration of association rules. So the people involved in this project are myself, Lucy, Andrea, Alain, Fabien, and Marco. And this is one of the subject of one of the papers we just had accepted in the InfoVis conference. So for those who don't know, an association rule is an application, is an implication that from X to Y. So if the idea is that X is an antecedent item set and Y is a consequent item set, indicating that transactions containing items in the set X tend to contain items in the set Y. So in our case, transactions are the publications and items will be the named entities that have been extracted from the publications. Like we can think of them like keywords in the publications. These association rules normally are described via some measures of interest. Typically, we have support and confidence. Support is the probability of finding the terms X and Y in a transaction, while the confidence is the probability of finding Y in a transaction, knowing that X is in the same transaction. And in this project, we have a new measure of interest that has been proposed by Lucy and Andrea. It's called interestingness. So this measure is the serendipity of the rule. So basically it penalizes the rules or named entities with high incidence in the data set. For instance, since we are working with a data set that talk about several kinds of viruses, the named entity virus will appear thousands of times in the dataset, and therefore it will appear in several rules because the rules are calculated based on the number of co-occurrences between two named entities in the publications. But considering the nature of the dataset, this information is not, could be considered not very relevant for the expert users. So the algorithm penalizes the rules that have the named entity virus in it, which doesn't mean that we are deleting them from the data. We are just, because the word can still be associated with a named entity that is more rare, which would result in a rule that is more interesting. And then we have also the symmetry measure that basically says if the rule works inversely. That means we have another rule where the antecedent is the consequent and vice versa. So to calculate the data set of association rules, we are using as an input data set for the algorithm created by Lucy and Andrea. I forgot to explain that we have two knowledge graphs in the COVID on the Web dataset. One is the named entities that have been extracted from the publications, and another one is argumentative graph. So we are using the one with the named entities, so the core-19 and EKG. And particularly, we are focusing on the named entities that have been identified and disambiguated using the Wikidata entity fishing tool. At the time of this project, the COVID on web dataset, we're using this 7th version of the Core 19 dataset that contained 50,000 publications. So to have an idea, today we have more than 200,000. So the mining process defined, well, as I said, transactions, publications, and item sets as named entities, and uses 4 clustering approaches to find. The idea is to use these clustering approaches to extract more interesting rules. So we have no clustering at all. We have items clustering, transactions clustering, and clustering of both items and transactions. And all of this information is also used as a filtering process in the visualization later on. The resulting set of association rules undergoes then a filtering process based on redundancy, minimal confidence, and interestingness. And then that results in a data set that contains 1,772 rules, the dataset we are using right now in the RVs application, and some measures of confidence, support, interestingness, and symmetry, which gives basically a table like this. So we have the antecedent item set, which contains 1 or 2 named entities inside, the consequent item set in measures of confidence, interesting, support, whether it's symmetric or not, and the cluster to which it belongs. So basically, if we have an input data set in this format, we can visualize the data from, well, any data set. Is not specific to this data set, not specific to COVID on the web. So the interest of using association rules, specifically in the COVID on the web data set, we were thinking about identifying correct errors in the database, because sometimes we could have some named entities that have not been correctly identified, something that it was already, some of them were already identified these errors while using the extracting the association rules, but with a visual aid, it would make it easier to find these problems. We could also identify relevant collections of publications in the database based on the co-occurrence of named entities. So let's say that we want to know whether coronaviruses and cancers are related. We can see whether there are rules that connect these two named entities, and then find the publications that talk about it to understand the relationship between them as well. And for that, we normally, when we are exploring association rules, we have a set of 6 exploratory tasks that we identified also in the literature that allows to answer this, to perform these explorations. For example, an overview of association rules, the possibility to identify interesting rules based on the measures of interest, the possibility to identify the relationships between the items, identify frequent item sets, compare association rules, and recover detailed information describing it. And what we could see in the literature is that, well, first of all, we don't have that many works that support the visualization of association rules, and most of them do not support at least 2 of those tasks. So for that, we propose RVs. So I'm gonna go to the application right now. So the application basically contains 3 visualizations. So we have a scatter plot that gives initially an overview of the rules based on measures of confidence and interestingness. And we are also using color, which describes, also in the other visualization we will see in the following, the measures of interestingness and confidence. So we see that when we have something that is more blue, it means that it's a rule with high confidence and high interestingness. If we have something tending to pink, it means that we have high confidence, but not necessarily high interestingness, and vice versa. When we have something tending to green, it means that we have rules with high interestingness, and low confidence. And also we are using a pattern with white dots to indicate whether the rules are symmetric or not. But here we can see, so we can see how many rules we have, and the distribution of those rules, but we don't know what items are included in these rules. So for that, we could, for instance, go to the circular paginated view of subsets, either directly by clicking on the tab or selecting one of those subsets here that are of interest. So for instance, here we have 29 rules. We can just explore this in the circular view. And this circular view shows around the circumference of, around this axis, shows all the named entities that are involved in that subset of rules. And then we have the ribbons connecting these named entities. And here we can also see the direction of the rule from antecedent to consequent. When we have this arrowhead here, it means that this named entity is the consequent of the rule. And when we don't have the arrowhead, it means it is the antecedent of the rule. And the color, again, following the same idea, the same bivariate legend, indicates measures of confidence and interestingness. Then from here, we could, because this is a visualization that allows to perform some tasks based on the rules. So even though we have the items, we are focusing mostly on the rules. If we want to focus on the items, for instance, I'm going to select here crystal structure, and I want to know all the rules that contains this named entity as the antecedent of it. So I can use now the exploratory graph view of items and say, show me all the rules that contain this named entity as the antecedent. And then I go to this third view here, where I have all the rules and all the other items that also are included in this rule, in these rules. I can also then choose other items of interest. I can also come here and choose something that I'm looking for, that I'm interested. For example, if I choose dyspnea, I see that we have in dataset only one rule that connects dyspnea and Middle East respiratory syndrome in coronavirus to cough. So we see that there are a link between among them. And I can also see then what papers are talking about this by clicking on the rule. This gives me some detailed information about the rule. So the detailed information about the interestings, the confidence support, whether it's symmetric or not, and the cluster it belongs to, and also the list of publications from the COVID-1 web dataset. And here we also have the DOI that allows us to go to the source and recover the paper if this is interesting for us. I'm going to come really back in the circular paginate view of subsets, because we can also start, we are not obliged to come from here. We can start directly in here. And the idea is that we cannot show all the rules in this circle because we have 800. And so here we are looking at 40 rules, and we can then go to the next 40, the next 40, or change here and show, for instance, only 20 if that's easier to read. The same way as we did in the graph view, we can also recover detailed information about it. So it takes a while because we are applying a query directly on this Sparkle endpoint. We can also filter the data. So here I'm looking at the rules that have been extracted from the clustering of papers, but I can also choose to look at the rules with no clustering or clustering of terms or cluster of both. And for helping the user, we have some information that shows what the papers in that cluster are about. And yeah, I think that's it for the RVs. Okay, the next one is then the LDVs interface. So it's a linked data visualizer. So as the name says, this is an interface that intends to visualize every linked data. So the idea is that we provide a generic visualization pipeline for linked data in a way that we can support automatic visualization of data extracted from any Sparkle endpoint that allows the user to create some meaningful data sets to perform their analysis We have today many other approaches that also support the visualization of linked data. But what we noticed is that, well, some of them, most of them, allow to visualize the RDF graph as it is. And although this is interesting and can support a number of tasks, we thought this is not enough because we cannot explore other information. We also have some solutions that allow to that create some visualizations based on the data type. But the problem is normally we have a Sparkle result set, for instance, and then it will give us only one visualization. But sometimes that's not enough to answer our questions, and especially when we are talking about exploratory tasks. So that's where LDVs enters. LDVs works in basically 3 steps. We have the query management interface that allows users to create queries that extract meaningful subsets of data to be explored. And then this data will go into a transformation engine that well, process the data and transform it in the format that we need to visualize using the DMG Explorer tool. So I'm gonna show you in details the 3 steps. So the first one is the query management interface. So we have basically two parts of it. We have the first part that is a list of predefined queries. So anyone can create a query and save there. That makes that next time we access the interface, we don't need to create again query and only play it and visualize the results using DMG Explorer. We can also view the query, edit, clone it so that we can create a new one using a query already existing. So that may help the creation of new queries. We can also delete, clear the cache, or also publish it. So when we publish a query, it goes to a vitrine where a user that doesn't have knowledge of Sparkle can use the tool to visualize the results of some of those predefined queries here. The second part is the query form. So here we can enter any Sparkle endpoint. We can give it the query a title, and then we enter the query here. So the system can visualize any subset of data that follows a certain standard for the query. So basically what we need, we have 3 mandatory variables. We have S, O, and P. Knowing that what we are looking for here, the result will be a graph. So basically S and O are the nodes of that graph, and P will be the link between the nodes that we can define as we want. Here, for instance, this query will return from the COVID on the Web Sparkle endpoint all the publications, or actually the co-authorship network created by the publications that are there. So what we have here is S and O are two researchers, 2 authors, and P is a publication. And then we can also give some optional variables to describe the edge, or in this case, the publication. So we have date, in this case will be the publication date, the label, which in our case is the title of the publication, and the type, which will be like conference or journal articles. Further, we have a space here for a style sheet. So the idea here is that the user can customize some parts of the initial graph, the initial node link diagram, such as the colors of the nodes, using a format like this one. So we can create some keywords here like FST and say that the color is light green. And then we have SND and say color is orange. And then we can link this, bind this to the query using something like this. So we say that FST is style 1, and then style 1 will be applied to S, and style 2 will be applied to O. So every value that is connected to S will be light green, and every value connected to O will be orange in the node link diagram. Further, we can use this style sheet to connect some services that we can further use to explore the data that we are already exploring in the DMG Explorer. So here, for example, we are using ACTA, the ACTA service, and also the Correct service. I'm going to show you later how this works. And then we have the actions. We can visualize the results using DMG Explorer. We can export those results to like for debugging, for instance. We can also export the transformed results. So this will be the data set that is the input of the visualization. And we can export the Sparkle query and save the changes we made in the query. So when we click here on visualize Sparkle query results, the result set is sent to the transformation engine, which consists on two parts. The first part is when we transform this Sparkle result set into the DMG Explorer data model. So one of the things we do, we will go search for these mandatory and optional variables, but we also create some measures that describe the nodes and the links, like the amount of publications per type, or the amount of publications between, or links between two nodes, etc. And then we have a second part that occurs while we are interacting with the visualization. We have a set of mappers that allow us to subset the input data of the visualization. And then it transforms this new subset of data so that we can visualize with different visualization techniques. And we have basically six, so far we have 6 visualization techniques. We have the node link diagram, which is the initial visualization. We have the cluster views that allow us to some clustering analysis. We have the iris visualization, which gives us information about pairwise relationships between an item that will be, or an author that will be in the center here, and then the relationship with all of the other items in the dataset. Similarly, the glyph matrix gives us this pairwise relationship between the items described by the attributes such as type of publications and amount. We have the bar chart that gives us the distribution of items over a certain attribute. And so far, well, for now, better, we are working with the temporal distribution of this information, and we have the listing that gives us the list of items, or in this case, the list of publications that were used to create this visualization. Then we have the DMG Explorer. So DMG Explorer was initially created to support the exploration of multidimensional graphs. And the idea is that we can define the input graph topology. So we can work with co-authorship, we can work with co-occurrence of keywords, for instance. I'm gonna show you some examples later. The idea is also that we can incrementally explore the data so that we can deal with large amount of data. We can also choose appropriate visualization techniques on the fly so that we can create new hypotheses and explore them appropriately. We can arrange the visualization space in meaningful ways. And we can retrace the analytical action. So one thing is that we represent visually with this line between the views, the dependency between views. So we know that, for example, the bar chart here, or the scatter plot, were created from a subsetting action that we did on the node link diagram. Another way of doing this retracing is using the history tree that is always displayed. That shows all the visualizations we used, even the ones we hide during the exploration process to clean and organize the visualization space. And then we can show them again if necessary and start a whole new exploratory path from that point in history. So we applied this visualization, we applied LDVs to already at least 4 Sparkle endpoints. So mostly scholarly article databases. First one is COVID on the Web, and then HAL and the Microsoft Academic Knowledge Graph, where we are exploring named entities or keywords co-occurrence, and also co-authorship networks. But we also apply to other RDF datasets, or in this case, DBpedia, to show that we can also display the RDF graph, as we can see here, to see what is inside. We can also explore the ontologies, like the hierarchy of classes, of properties, and the signature of properties. So that we can, again, to understand the data we are dealing with. And also to explore RDF graph summarization, so that you can get an idea of the structure of the RDF graph without visualizing all the instances. And also to do visual mining of RDF graphs, as we did with the Scholarly article database. So I'm going to show you now how this works. It's a little problematic to change. Yes. So one of the things, the first thing is we can see the co-authorship network within the publications about coronavirus. So this is using the COVID on the web dataset. So what we have here is nodes are authors that are connected between them through publications. And then we can go further and see exactly what is the relationship between them. So here with the iris, for instance, we can see with whom we have a certain author has the most collaborations. And then we can see what are those papers. And we have here the list of all the papers. We can also have normally the distribution on over time. So we see that the publications were in 2015, 2016. We can also see with the cluster Vs with the subclusters that exist within this group of co-authors. So we can see here, for instance, we have those people working together, also those, and so on. And here there is also something quite interesting, is that we can go back to the source of the data here directly on the COVID on the web dataset. Another example, sorry again about this, would be the co-occurrence of named entities. So here is cancer and coronaviruses. And we are using the style sheet I talked about to color all kinds of coronaviruses in orange and all kinds of cancers in green. So that we can see directly here the relationship between them. And here I've added this, the possibility of going to the CURES or also the ACTA. So if I go to the list of papers, for instance, I can here choose to explore the argumentative graph of this publication using ACTA. So this might take a while, but this is the same one I've opened before. So that will give me then the interface in ACTA so that I can further explore the data in a different perspective. Yeah, I think that's it for me. Thank you. It was a little fast, so if you have any questions, please don't hesitate.